Hey there, chemists. Today we're going to talk about salt solubility. And as a reminder, the word salt in chemistry is a very generic term. It doesn't refer specifically to like sodium chloride. It can be used for any ionic compound. And so we're focusing on salt solubility in water, on whether or not if we mix a particular ionic compound, it will dissolve in water. And lots of ionic compounds do dissolve in water very well because of the polar nature of water and then their own ionic charges being attracted to those partial positives and negatives in the water molecule. But not all. So for example, I have two different salts here, sodium carbonate and calcium carbonate. If you wanted, you could pause and practice turning those ionic names into ionic formulas. It's good practice for our upcoming tests and quizzes. One of these is soluble in water and one is not, and you cannot tell just by looking at it. They're both white crystalline solids, pretty indistinguishable just looking. So how are we going to know from a name or chemical formula whether or not something is going to dissolve in water? Well, I mean, in some ways you just have to kind of test it. But as chemists have tested solubility of various ionic compounds, some patterns have emerged, and from that we've been able to generate some kind of generic solubility rules. And we want to use that word rule very loosely, of course. As you guys are already learning, there are always exceptions. Another thing is you do not need to memorize the solubility rules. You will be provided with a solubility rule chart like this, pretty much this identical one, on a test or quiz. So if you're in a face-to-face class for test or quizzes, you would be provided one on the day of. And if you're in an online class, you would print your own from the, you'll be provided it and print it, and then you can show that it's blank when you go to do your authentication stuff for honor lock. So this is really more about not memorizing the list, but how do I use it? So let's go through a couple examples, and it will help us determine if the salt is likely to be soluble in water. Now, soluble in other substances is a different chart. We won't get into that. So here I have, practice your naming. What's the name of this? This is lithium phosphate. You know that polyatomic ion name there. So if I'm going to determine whether or not lithium phosphate is likely to be soluble in water, I want to start by looking at the cation, and that's the first one listed. It's usually a metal, so lithium. And I want to check that first because you'll see in this very first category, soluble cations, it says that group 1 metallic ions and then that polyatomic ion ammonium are soluble with no exceptions. So what that means is they're soluble regardless of the anion in the salt, in the ionic crystal lattice structure. So I'm done with lithium phosphate. Lithium phosphate is soluble in water. So that means it will dissolve. If I gave you a sample of lithium phosphate, you'd be able to mix it up and dissolve it well in water. So lithium phosphate is soluble in water. Let's look at another one. So again, practice, can you turn this into a name? Pause if you need to. This is calcium hydroxide. So calcium hydroxide. Now when I look at the cation, calcium, and I locate it on the periodic table, I have a periodic table above me here, that's why I look up when I talk about it, you'll see it's a group 2, so it's not in this group. And you might even be going like, I don't really even see it here. I see it here, but I don't have sulfate as my anion. So once you've checked your cation to make sure it's not one of those always soluble, no exceptions, then you want to look at your anion. That's the negatively charged one. And in this case, our anion is one of our polyatomic ions, hydroxide. And I find it down here in this group of usually insoluble. So insoluble means it won't dissolve. So don't get those words confused, even though they're so similar. Usually insoluble. So hydroxide salts are usually insoluble, and what you want to check is in terms of exceptions, we actually already have. The calcium is group 2, it's not one of the exceptions. So calcium hydroxide is not particularly soluble in water. It might be able to get a little bit of it to dissolve, but not very much, so we classify it then as an insoluble for water ionic compound. So one more, let's look at magnesium chloride. So I always check my cation first to see if, because then I'm done if it happens to be one of the always soluble. But magnesium, just like calcium, is an alkaline earth metal, not a group 1 metal. It's group 2. So I don't get to be done right away. So next I check my anion. I have chlorine. So chlorine is right here. And chlorine is usually soluble. So that means it usually will dissolve in water. So it's a usually insoluble anion. It does have some exceptions though. And so I do want to double check to make sure that the cation that it's bound to is not one of the exceptions. Silver, mercury, or lead. Now it's not, so it is safe to assume that this is soluble in water. But if it was one of the exceptions, silver, mercury, or lead, then even though it's usually soluble, I would say that it is insoluble in this case. So let's go back then to our solubility question. Which one of these is going to be soluble in water, sodium carbonate or calcium carbonate? And you probably already, without referring back to your table, are going, wait a minute, that's a group 1, no exception. So let's go ahead and relook at it real quick though. We have carbonate is usually insoluble, and they both contain the polyatomic ion carbonate. But that first one contains one of our group 1 metallic ions. So sodium carbonate is soluble in water, and calcium carbonate is not. Calcium carbonate is actually pretty much what chalk is made out of. So if you ground up a piece of chalk and tried to dissolve it in water, it would just stay this like milky white, and eventually it would settle out because it is insoluble. Now remember, as you've hopefully already learned, when ionic compounds, when salts do dissolve in water, there's a really particular thing that happens in that the ionic bonds are actually broken. The water pulls the ions apart, and the ions separate from each other and spread throughout the water. And I think it's really important, even though we might write it as like NaCl and then we have the AQ, aqueous, next to it, we need to understand, we need to mentally translate that into realizing that they're actually dissociated. They're not next to each other. They're spread throughout the water, engaged in, I always kind of think of it as this big dance party, you know, dance with this water molecule and then get pulled away and dance with this, and they're spread throughout. And that's what the dissolving of an ionic compound looks like. So let's do a little bit of practice. I have 3 practice problems here. Use your solubility rule chart, or the one provided in the book, to identify whether or not each compound would be soluble in water. If it is, we're going to do an extra step. Write the dissociation equation, which you learned about a little bit earlier. So write the dissociation equation. So I would really encourage you, as always, to pause the video here and try to do these on your own. And if you get stuck, watch a little bit more till you get unstuck, because we want your brain to have to retrieve that information. So I need to get my pen working real quick. Where is my pen and why is it not working? There we go. Okay, so you didn't need to pause the video, you just needed to wait for me. So if you look back on your chart, you're going to see that potassium is one of those always soluble, no exceptions. So to the first part, yes, this is soluble in water. So what would that dissociation equation mean? So what am I talking about here? So what I mean is, I'm just going to use this part's already done. So potassium phosphate solid dissolves in water. And I might write that in a chemical equation just as potassium phosphate with an AQ, but my dissociation equation shows them as those dissociated ions. And that creates 3 potassium ions dissolved in water for every 1 phosphate ion dissolved in water. So there's my AQ. So you'll notice that the 3 here comes in front, the coefficient comes in front, and that I do include the charges. And the reason for that is these 3, they're not bound together. They're spread way throughout the water. They're nowhere near each other. They're not bound in a crystal lattice structure anymore with the phosphate, but we do want to reflect the appropriate ratio that we were reflecting over in our chemical formula. Sorry, lost my train of thought. Another thing, you'll notice that we do include the charges, and sometimes this is weird for students because we don't write the charges over here in the chemical formula, and then we do over here, and that seems kind of strange. The reason for that is really the chemical charge is implied in this formula by the presence of the phosphate. So when another chemist looks at this and they see, and they're like, oh, this is a positive and this is a negative, and they know that phosphate is, they know the charge of phosphate, and they know, or it can infer the charge of potassium from that. So the metal next to this negative polyatomic ion implies those charges. When they're not there, we have nothing to assume. You could have a chemical equation that had solid potassium. And solid potassium is not the same as potassium ions dissolved in water. They're very, very different. And so without that polyatomic ion right next to it, without the negative one that's also in the chemical formula, we're going to include those pluses to identify that it is the ion, not the atom of the element, not the neutral atom of potassium, which is a completely different thing. It is the ion. So in continuing, we have then silver bromide. I'm practicing my naming. And if you locate your bromide on your chart, you'll see that it is usually soluble except, and this is one of the exceptions. Silver is one of the exceptions. So silver bromide is not soluble in water. So you try to dissolve it in water and it's just going to stay. So AgBr solid becomes AgBr solid. It's not soluble in water. So here we have our ammonium hydroxide, and on this one I gave you the name instead of the chemical formula, so you could practice turning a name into a chemical formula. So, whoops, I'm starting to write. Still getting used to my pad here. So ammonium hydroxide, and ammonium, the cation, that's our only positive polyatomic ion that we have to learn, is in that first group along with the alkali metals. It is always soluble, no exceptions. So yes, this is soluble in water. So when it dissolves in water, so this is the solid, and then I put it into the water, and it becomes the ammonium ion. So I'm going to include the charge now. Dissolved in water, plus the hydroxide ion, dissolved in water. Sorry, I had to move up a little bit. So the water is not strong enough to separate the covalent bonds that hold our polyatomic ion together. So the nitrogen isn't going to separate from the hydrogen, or the oxygen from this hydrogen. It's this ion separates from this ion, and that's how we write that dissociation equation. So let me know if you guys have questions, and good luck.